It all started with a need. A merchant needed to move wool across the channel. A king needed to move soldiers. A fisherman needed to feed his village. The ship wasn't a project, it was a solution. And the solution began not at the water's edge, but deep in the forest. The master shipwright was the key. He wasn't an architect with paper plans and complex mathematics, he was a craftsman. He held the entire design in his head, a combination of tradition, experience, and instinct. He could look at a customer and listen to his needs, then picture the vessel that would do the job. He knew the shape of a hull that could handle rough seas. He knew the size of a cargo hold for a certain amount of wine barrels. This knowledge was his trade secret, passed from father to son, from master to apprentice. Sometimes they made a small model. A half-hull model, carved from a block of wood, could show the owner the ship's lines. It helped visualize the final product, but the real blueprints were in the shipwright's mind and hands. He made decisions by eye, judging curves and angles as the work progressed. The eye of the master was a real and respected skill. Once the design was settled, the hunt for wood began. This was the most critical part of the entire process. The right wood made a strong ship. The wrong wood made a wreck. Oak was king. It was strong, dense, and resistant to rot. Shipwrights wanted oak for the most important parts of the ship, the keel, the frames, and the main planking. It was the backbone and the bones. But not just any oak would do. They needed specific shapes. A ship is all curves. You can't build a curved hull from straight planks without a lot of work. So shipwrights didn't just look for trees, they looked for shapes within trees. They would search the forest for trees with natural curves in their trunks and major limbs. These were called compass timbers. A large, bent branch could become a frame, or a rib, of the ship. A tree root that grew out at a right angle from the trunk was perfect for a knee, a natural bracket used to strengthen the joints between the deck beams and the hull. Finding these pieces was an art. The shipwright or his team would spend weeks or months in the woods marking trees. They were looking ahead, seeing the parts of the ship that lay hidden in the living wood. This meant a single ship was a puzzle made from dozens of different trees, each chosen for a specific purpose. For other parts, other woods were used. Pine was tall, straight, and relatively light. It was perfect for masts and spars. Elm was tough and resisted splitting, and it held up well in water, so it was sometimes used for the keel. Once the trees were chosen and felled, the hard work of processing began. The logs were massive and heavy. They were moved with oxen and human muscle, dragged to a river to be floated or hauled directly to the shipyard. At the yard, the logs were converted into usable timber. The main tool for this was the pit saw. This was a long, two-man saw. One man, the top dog, stood on the log, guiding the saw from above. The other man, the underdog, stood in a pit below, pulling the saw down. It was exhausting, back-breaking work, and the man in the pit was constantly covered in sawdust. The wood wasn't used right away. Green wood, wood that is freshly cut, is full of moisture. If you build with it, it will warp, shrink, and twist as it dries. This would tear a ship apart. So, the timber had to be seasoned. It was stacked carefully, with air gaps between the pieces, and left to dry slowly. This could take years. A major shipyard would have huge stacks of timber seasoning, a long-term investment in future ships. They were always thinking several years ahead. The shipyard itself was a chaotic, noisy place. It was always near the water, on a sloping piece of ground that made launching the finished ship easier. It wasn't a factory with a roof. It was an open-air workshop. You would hear the constant thud of axes and adzes, the rhythmic groan of the pit saw, and the clang of the blacksmith's hammer. The air would smell of fresh-cut wood, hot tar, and the sea. The tools were simple and effective. The axe felled the tree. The adze, an axe-like tool with the blade set at a right angle to the handle, was used for shaping and smoothing timbers. It was the shipwright's primary sculpting tool. Saws cut planks, augers drilled holes, hammers drove nails and pegs. At the shipyard's forge, a blacksmith made all the iron parts, nails, bolts, anchors, and fittings. Everything was made by hand, on site. Building a ship was a community effort, employing dozens of men with different skills, all orchestrated by the master shipwright. With the wood prepared and the site ready, the physical work of building the ship began. The ship started not as a whole, but as a single piece of wood laid upon blocks. This was the keel. The keel was the spine of the vessel. It was the foundation upon which everything else would be built. It was usually a massive, long piece of oak, sometimes scarfed together from several pieces to get the required length. Getting the keel right was everything. It had to be straight and strong. At each end of the keel, two more crucial pieces were attached. At the front was the stem, the curved piece of timber that would form the ship's bow. At the back was the sternpost, the upright piece that would form the rear. These three pieces, keel, stem, and sternpost, created the basic profile of the ship. They were the first lines of the drawing made real. From this point, medieval shipbuilding went in two very different directions. The method you used depended on where you were in Europe. In the north, in Scandinavia and around the Baltic Sea, they used the clinker method. In the south, in the Mediterranean, they used the carvel method. They were fundamentally different ways of thinking about how to build a boat. The clinker method, which the Vikings perfected in their longships, was a shell-first construction. This means they built the skin of the ship first. After the keel was laid, they attached the first row of planks, one on each side. This was called the garboard strake. Then they added the next row of planks, but they didn't place it edge to edge. Instead, they overlapped it on the plank below, like siding on a house. This overlapping seam is the defining feature of a clinker-built boat. Each plank was fastened to the one below it. The Vikings used iron rivets. They would drill a hole through both overlapping planks, push a long iron nail through from the outside, and on the inside, a man would hold a small metal plate called a rove over the end of the nail. The man on the outside would hammer the nail head, and the man on the inside would use another hammer to flatten the end of the nail over the rove. This clenched the planks together tightly. They would do this every few inches, all along the length of the plank. They built the hull up plank by plank, creating a flexible wooden shell. It was a bit like weaving a basket. The shape of the boat was created by the shape of the planks. Each plank had to be carefully cut and shaped with an adze to create the vessel's curves. It was a highly skilled job. Only after the shell of the hull was mostly complete did they add the internal frames, the ribs of the ship. The frames were fitted into the existing hull and fastened to the planks, giving the flexible shell its strength and rigidity. This clinker method created ships that were light, strong, and flexible. A clinker-built longship could twist and bend in the waves of the North Atlantic, absorbing the energy of the sea instead of fighting it. They were also shallow, which meant they could be rowed up rivers and pulled ashore on beaches. This was perfect for raiding and exploration. The famous medieval cog, a trading vessel of the Hanseatic League, was also clinker-built. The carvel method, common in the Mediterranean, was the opposite. It was a skeleton-first construction. After laying the keel, stem, and sternpost, the shipwright would build the entire internal frame of the ship. He would erect all the ribs, or frames, attaching them securely to the keel. When he was done, the structure looked like the skeleton of a great whale sitting on the stocks. Only when this complete skeleton was finished did they begin to add the planks. And they did it differently. Carvel planks were fitted edge to edge. They did not overlap. This created a smooth outer surface. Getting a tight fit between these planks was a major challenge. Each plank had to be perfectly shaped to fit against its neighbors and follow the curve of the frames. Instead of iron rivets, carvel builders often used wooden pegs called treenails, sometimes pronounced trunnels. A hole was drilled through the plank and into the frame beneath. Then a long, seasoned wooden peg, usually oak, was hammered tightly into the hole. A small wedge might be driven into each end of the treenail to expand it and lock it in place. The beauty of the treenail was that when it got wet, it swelled, creating an even tighter fit. A wooden peg also flexed with the hull in the same way the planks and frames did, which made for a more durable fastening than a rigid iron spike, which could work its way loose over time. The carvel method had huge advantages. Because the strength came from the heavy internal skeleton, carvel ships could be built much larger than clinker ships. A bigger ship could carry more cargo, which meant more profit for a merchant. It could also carry more men and more weapons, including cannons, for a king. The smooth hull was also more efficient in the water. Over the course of the later Middle Ages, the carvel method slowly spread north. It was the future of shipbuilding. It allowed for the development of the carracks and caravels that would eventually sail across the oceans of the world. But both methods required immense skill to execute. Whether building clinker or carvel, the next major stage was planking. This was the process of creating the ship's skin. It was a job that turned rough lumber into a graceful, curving, and watertight surface. It was where the ship truly began to take on its final form. The planks themselves did not start out as neat machine-cut boards. They were hewn from logs. A shipwright could get 2, maybe 4, good planks from a single log. They were often radially sawn or split, which followed the grain of the wood. This made them incredibly strong and resistant to warping. This was much more wasteful of wood than modern sawing methods, but it produced a superior plank. Shaping these planks was the work of a master craftsman using his adze. He stood on the plank and swung the adze between his legs, the curved blade chipping away wood with each stroke. He could make a plank thicker in the middle and thinner at the ends. He could bevel the edges precisely. He controlled the shape and thickness with incredible accuracy, all by eye and feel. The biggest challenge was bending the planks to fit the curve of the hull. A ship has complex curves, bending in 2 or even 3 directions at once. The wood had to be forced to follow these lines. Medieval shipbuilders did not have the steam boxes of later centuries. Their method was more direct fire and water. A plank would be soaked in water, sometimes for days in a pond or a long trough. Then, it would be propped up over a slow-burning fire. The combination of heat and moisture made the wood fibers pliable. It was a delicate balance. Too much heat, and the plank would scorch and weaken. Too little, and it wouldn't bend. As the plank heated up, a team of men would work together to bend it into place against the frames or the previous plank. They used a system of levers, wedges, and clamps. A large wooden clamp called a span shackle might be used to force the plank into a tight curve. They would pull and push, shouting instructions, until the plank was snug in its intended position. Then they would fasten it quickly before it cooled and stiffened. This process was repeated for every single plank on the hull, from the keel to the rail. In the clinker tradition, fastening the planks was a 2-man job of riveting. As the hull grew upwards, plank by overlapping plank, the shipwrights would constantly check its shape. They might use a long, flexible strip of wood, a batten, to check the fairness of the curves, ensuring a smooth and flowing line. The shape of the boat was a direct result of the shape of each plank. A mistake in one plank would be magnified in the next. In the carvel tradition, the process was different. The skeleton was already there, so the planks just had to be fit to it. But fitting them edge to edge was a challenge. Each plank had to be shaped perfectly to lie flush against its neighbor above and below. The shipwrights would use tree nails to fasten the planks to the frames. They would drill a hole through the plank and deep into the thick frame behind it. Then they would hammer the oversized tree nail home. The end would be cut off flush with the plank. This process created a hull that was a mosaic of wood. The shipwright had to know how wood behaved. He had to account for how it would swell when it hit the water. The seams on a new Carvel-built ship might look a little gappy on land. But the builders knew that once the ship was in the water, the planks would absorb moisture and swell, closing the seams tight. And it was a planned imperfection. The final planks at the top of the hull were the shear strikes. They defined the final sweeping line of the ship's deck. Below, near the keel, the garboard strake was the first and most important plank, forming the joint between the keel and the rest of the hull. In between were dozens of other planks, each one individually shaped, bent, and fastened. It was a slow, laborious process that took a team of skilled men many months. The result was a hull, a wooden shell ready for the next stage of its transformation into a seafaring vessel. A planked hull was the shape of a ship, but it was not yet a ship. It was a wooden vessel full of holes. Every seam between the planks was a potential leak. The wood itself was vulnerable to the sea. The next stage was about making the ship watertight and strengthening its structure, turning a fragile shell into a robust machine for sailing. This process was called caulking. The goal of caulking was to stuff the seams between the planks with a waterproof material to stop leaks. This was especially critical for carvel-built ships with their edge-to-edge planking. Clinker-built boats had overlapping planks, which were naturally more water-resistant, but they still needed some sealing. The material used for caulking was called oakum. Oakum was made from old rope. Sailors would painstakingly unpick the strands of old tarry hemp ropes, separating them into loose fibers. This recycled material was then twisted into thin strands. The caulker's job was to hammer this oakum into the seams. He used special tools, a caulking iron and a mallet. The caulking iron looked like a blunt chisel. He would lay a strand of oakum over a seam and then use the mallet to strike the iron, driving the fibers deep into the gap between the planks. He would do this inch by inch, yard by yard, along every single seam on the entire ship, inside and out. It was a noisy, repetitive job that required a specific rhythm and force. Too little oakum, and the seam would leak. Too much, and you could force the planks apart, weakening the hull. A skilled caulker could tell by the sound and feel of his mallet when the seam was perfectly packed. After the seams were filled with oakum, they needed to be sealed over. This was done with pitch, a black, sticky substance made from pine resin. The pitch was heated in a large pot over a fire until it was a bubbling liquid tar. Then it was paid into the seams over the oakum using a ladle or a brush. This created a final waterproof seal that was flexible enough to move with the ship. But the work didn't stop there. The entire hull, both inside and out, had to be protected. The wood in sea waters under constant attack. Tiny marine organisms called shipworms could bore into the wood, turning strong timbers into a honeycomb of tunnels in just a few years. Rot was a constant enemy. To combat this, the entire vessel was coated with a protective layer. This was a foul-smelling mixture, often based on pine tar, but it could also include things like tallow animal fat or sulfur. This mixture was heated and painted over every square inch of the hull. It was hot, messy, dangerous work. The smell was overpowering. The tar would get on everything. But this foul-smelling coat was the ship's armor. It repelled water, killed marine borers, and preserved the wood. A ship had to be retarred regularly throughout its life to keep it seaworthy. With the hull sealed, the next step was to add internal strength. The hull was still just a large open shell. The pressure of the water from the outside and the weight of the cargo and mast from the inside would try to change its shape. To hold it all together, the builders installed the deck beams. These were large, strong timbers that ran from one side of the ship to the other. They were the floor joists for the deck, but their most important job was to keep the sides of the ship from being pushed inward or pulled outward. They locked the hull's shape. To secure the deck beams, they used knees. A knee was a natural L-shaped bracket made from a piece of wood where a large tree root grew from the trunk. This gave it immense strength because the grain of the wood followed the curve. These knees were fitted into the corners between the deck beams and the ship's frames, providing critical reinforcement. They were bolted or pegged in place, making the entire structure incredibly rigid. Finally, they would build the deck itself. Planks were laid over the deck beams, caulked and sealed just like the hull. Hatches were cut to provide access to the cargo hold below. The ship was now a sealed, strengthened structure. It was no longer just a collection of parts. It was a unified, solid vessel ready for its mast, its sails, and its launch into the water. The hull was complete, but it was an empty, powerless thing. The final stage of construction was to give it power and control the mast, the sails, the rigging, and the rudder. This was what would turn a floating container into a true ship. Stepping the mast was a major event. The mast was a huge, heavy pole, often the single largest piece of timber in the entire ship. It was usually a whole pine tree, chosen for its height and straightness, stripped of its branches and bark, and smoothed. Getting this massive spar into the ship and standing it upright was a serious challenge. It required careful planning and a lot of manpower. The mast had to sit in a special block of wood on top of the keel, called the mast step. This block had a square hole carved into it to receive the base of the mast. The mast also had to pass through a hole in the deck, which was reinforced with a framework called the partners. These 2 points, the step and the partners, held the mast securely. Using a system of ropes, poles, and sheer brute force, the workers would slowly hoist the mast upright and guide its base down through the deck and into the mast step. It was a slow, tense process. A mistake could send the massive timber crashing down, destroying weeks of work. Once the mast was stepped, it had to be supported. A mast by itself cannot stand up to the force of the wind. It needs a web of ropes to hold it in place. This is the rigging. There are 2 kinds of rigging. The first is the standing rigging. These are the thick, heavy ropes that are fixed in place. Their only job is to support the mast. The ropes that run from the top of the mast down to the sides of the ship are called shrouds. The ropes that run from the top of the mast down to the bow and stern are called stays. This network of ropes held the mast steady against the powerful push of the wind. Standing rigging was made of thick hemp rope, thoroughly soaked in tar to protect it from the weather. The second kind is the running rigging. These are the ropes that move. They are used to control the sails. The halyard is the rope used to haul the yard and sail up the mast. The sheets are the ropes used to control the corners of the sail, trimming it to the wind. The running rigging was generally not tarred because it needed to be flexible to run through blocks and pulleys. The sails themselves were a major expense. They were made from canvas, a tough cloth woven from flax or hemp. Sailmakers working in large lofts would sew many smaller strips of canvas together by hand to create one large sail. This was painstaking work. The seams had to be strong to withstand the force of a gale. Early medieval ships, like the Viking longship or the cog, had a single large square sail on a single mast. This was simple and powerful for sailing with the wind behind you, but it was not very good for sailing into the wind. In the Mediterranean, a different kind of sail was common, the lateen sail. This was a triangular sail that was much more efficient at sailing against the wind. One of the great innovations of the late Middle Ages was the development of ships like the carrack, which combined both types of sails. It might have a square sail on the main mast and a lateen sail on a smaller mast at the stern. This gave the ship much more versatility and power. Another critical innovation was the rudder. Early northern ships were steered with a large oar, called a steerboard, mounted on the side of the ship near the stern. This worked, but it was awkward, especially on a large ship in a heavy sea. The sternpost rudder was a major improvement. This was a rudder hinged directly onto the sternpost, controlled by a tiller. It provided much better steering control and allowed ships to become even larger. With the mast rigged, the sails bent on, and the rudder hung. The ship was nearly finished. The final touches were added, anchors were brought aboard, coils of rope were stored, and any cabins or shelters on deck were completed. The last act was the launch. This was a moment of great celebration and great anxiety. The ship had been built on land, sitting on blocks and props. Now it had to be moved into the water. The ground beneath the ship was prepared with a series of greased timbers, called ways, that sloped down into the water. On the launching day, the community would gather. The workers would knock away the last of the supporting block. With a great creak and a groan of timber, the ship would begin to slide. It would pick up speed, sliding down the ways and hitting the water with a huge splash. For the master shipwright, this was the final test. Did it float? Did it sit level in the water? Were there any major leaks? Seeing the ship he had pictured in his head months or years ago now floating in the harbor was the culmination of all his work. It was no longer just a collection of wood and rope. It was alive. It was ready for the sea.